Let's continue to read the book by Brian Greene, Until the End of Time. Chapter 2, The Language of Time, Past, Future, and Change. On the evening of January 28, 1948, nestled between a performance of the Schubert Quartet in A minor and a presentation of English folk songs, BBC Radio broadcast a debate between one of the most potential intellectual forces of the 20th century, Bertrand Russell, and Jesuit priest Frederick Copstone. The topic, the existence of a God. Russell, whose innovative writings in philosophy and humanitarian principles would earn him the 1950 Nobel Prize in Literature, and whose iconoclastic political and social views would earn him a pink slip from both Cambridge University and the City College of New York, provided numerous arguments for questioning, if not rejecting, the existence of a creator. One line of thought that informed Russell's position is relevant to our exploration here. Quote, so far as the scientific evidence goes, end quote, Russell noted, quote, the universe has crawled by slow stages to a somewhat pitiful result on this earth, and is going to crawl by still more pitiful stages to a condition of a universal death, end quote. With such a bleak outlook, Russell concluded, quote, if this is to be taken as evidence of a purpose, I can only say that the purpose is one that does not appeal to me. I see no reason, therefore, to believe in any sort of a God, end quote. The theological thread will be stitched into later chapters. Here, I want to focus on Russell's reference to scientific evidence for universal death. It comes from a 19th century discovery with roots as humble as its conclusions are profound. By the mid-1800s, the Industrial Revolution was in full swing, and across a landscape of mills and factories, that the steam engine had become the workhorse driving production. Nevertheless, even with the critical leap from manual to mechanical labor, the efficiency of the steam engine, the useful work performed compared to the quantity of fuel consumed, was meager. Roughly 95% of the heat generated by burning wood or coal was lost to the environment as a waste. This inspired a handful of scientists to think deeply about the physical principles governing steam engines, seeking ways to burn less and get more. Over the course of many decades, their research gradually led to an iconic result that has become just famous, the second law of thermodynamics. In highly colloquial terms, the law declares that the production of waste is unavoidable. And what makes the second law vitally important is that while steam engines were the catalyst, the law is universally applicable. The second law describes a fundamental characteristic inherent in all matter and energy, regardless of structure or form, whether animate or inanimate. The law reveals loosely again that everything in the universe has an overwhelming tendency to run down, to degrade, to wither. Stated in these everyday terms, you can see where Russell was coming from. The future seemingly holds a continued deterioration a relentless conversion of a productive energy into useless heat, a steady draining, so to speak, of the batteries powering reality. But a more precise understanding of the science reveals that this summary of where reality is headed obscures a rich and nonsensed progression, one that has been underway since the Big Bang and will carry onward to the far future. I was a little bit hesitant because I don't think I pronounced the nuanced, that word correctly, a rich and nuanced progression. It is a progression that helps explain our place in the cosmic timeline, clarifies how beauty and order can be produced against a backdrop of degradation and decay, and also offers potential ways, exotic though they may be, to sidestep the bleak end Russell envisioned, as it is this very science involving concepts such as entropy, information, and energy that will guide much of our journey. It is worth our while to spend a little more understanding it more fully. Next section, titled Steam Engines. Far be it from me to suggest that the meaning of life will be found lurking in the sweaty depths of a clamorous steam engine, but understanding the engine capacity to absorb heat from burning fuel and use it to drive recurrent motion in a locomotive's wheels or a coal mine's pump proves indispensable to grasping how energy of any sort and in any context evolves over time, and the way energy evolves has a deep impact on the future of a matter, mind, and all structure in the universe. So let's descend from the lofty realms of life and death and purpose and meaning to the incessant choking and clunking of 18th century steam engine. The scientific basis of the steam engine is simple but ingenious. Water vapor, steam, expands when heated, and so push afterward. A steam engine harnesses this action by heating a canister filled with steam that is capped by a snugly fitting piston free to slide up and down along the canister's inner surface. As the heated steam expands, it pushes forcefully against the piston, and that afterward thrust can drive a wheel to turn, or a mill to grind, or a loom to weave. Then, having expended energy through this afterward exertion, the steam cools and the piston slides back to its initial position, where it stands ready to be pushed when the engine is heated again, a cycle that will repeat so long as there is a burning fuel to heat the steam anew. While history records the steam engine's central role in the Industrial Revolution, the questions it raised for fundamental science were just as significant. Can we understand the steam engine with mathematical precision? Is there a limit to how efficient its conversion of heat into useful activity can be? Are there aspects of the steam engine's basic processes that are independent of the details of mechanical design or materials used and thus speak to universal physical principles? In puzzling over these issues, the French physicist and military engineer Sadi Carnot launched the field of thermodynamics, the science of heat, energy, and work. You wouldn't have known it from sales of his 1824 treatise, Reflections on the Motive Power of Fire. But while slow to catch on, his ideas would inspire scientists over the course of the following century to develop a radically new perspective on physics. Next section, a statistical perspective. The traditional scientific perspective, handed down in mathematical form by Isaac Newton, is that the physical laws provide ironclad predictions for how things move. Tell me the location and the velocity of an object at a particular moment. Tell me the forces that are acting upon it, and Newton's equations do the rest, predicting the object's subsequent trajectory. Be it the moon pulled by Earth's gravity or a baseball you just whacked toward center field, observations have confirmed that these predictions are spot-on accurate. But here is the thing. If you took high school physics, perhaps you will recall that when we analyze the trajectories of macroscopic objects, we generally, if quietly, invoke a great many simplifications. From the moon and the baseball, we ignore their internal structure and imagine that each is just a single massive particle. It's a coarse approximation. Even a grain of salt contains about a billion molecules, and that is, well, a grain of salt. Yet, as the moon obeys, we generally don't care about the jostling motion of one or another molecules inhabiting the dusty sea of tranquility. As the baseball soars, we don't care about the vibration of one or another molecule residing in its core. The overall movement of the moon or the baseball as a whole is all we are after. And for that, applying Newton's laws to these simplified models, does the trick. These successes highlight the challenge faced by 19th century physicists concerned with steam engines. The hot steam pushing against the engine's piston comprises an enormous number of water molecules, perhaps 1 trillion particles. But we can't ignore this internal structure as we do in our analysis of the moon or the baseball. It is the motion of these very particles slamming into the piston, bouncing off its surface, hitting the walls of the container, streaming back toward the piston again, that lies at the heart of the engine's workings. The problem is that there is no way that anyone, anywhere, however smart they may be and however formidable the computers they may use, can calculate all the individual trajectories followed by such an enormous collection of water molecules. Are we stuck? You might think so, but as it turns out, we are saved by a change in perspective. Large collections can sometimes yield their own powerful simplifications. It is surely difficult, impossible really, to predict exactly when you will next sneeze. However, if we broaden our view to the larger collection of all humans on Earth, we can predict that in the next second there will be roughly 80,000 sneezes worldwide. The point is that by shifting to a statistical perspective, Earth's large population becomes the key, not the obstacle, to predict power. Large groups often display statistical regularities absent at the level of the individual. An analogous approach for large groups of atoms and molecules was pioneered by James Clerk Maxwell, Rudolf Clausius, Ludwig Boltzmann, and many of their colleagues. They advocated jettisoning detailed consideration of individual trajectories in favor of statistical statements describing the average behavior of large collections of particles. They showed that this approach not only makes calculations mathematically tractable, but the physical properties it can quantify are the very ones that matter most. The pressure pushing on steam engine's piston, for instance, is hardly affected by the precise path followed by this or that individual water molecule. Instead, the pressure arises from the average motion of the trillion upon trillions of molecules that slammed into its surface each second. That's what matters. And that's what the statistical approach allowed the scientists to calculate. In our current era of political polls, population genetics, and big data more generally, the shift to a statistical framework might not sound radical. We have grown accustomed to the power of statistical insights extracted from studying large groups. But in the 19th and early 20th century, statistical reasoning was a departure from the rigid precision that had come to define physics. Bear in mind, too, that up through the early years of the 20th century, there were still well-respected scientists who challenged the existence of atoms and molecules, the very basis of a statistical approach. Notwithstanding the naysayers, it didn't take long for statistical reasoning to prove its worth. In 1905, Einstein himself quantitatively explained the jittery motion of pollen grains suspended in a glass of water by invoking the continual bombardment by H2O molecules. With that success, you had to be one heck of a contrarian to doubt the existence of molecules. What's more, a growing archive of theoretical and experimental papers revealed that conclusions based on statistical analysis of large collections of particles, describing how they bounce around containers and thereby exert pressure on this surface, or acquire that density, or relax to that temperature, matched data to explicitly that there was simple no room to question the explanatory power of the approach. The statistical basis for thermal processes was thus born. This was all the great triumph and has allowed physicists to understand not only steam engine, but also a broad range of thermal systems, from Earth's atmosphere to the radar corona, to the vast collection of particles swarming within a neutron star. But how does this relate to Russell's vision of the future? His prognostication of a universe crawling toward death. Good question. Hang tight. We're getting there. But we still have a couple of steps to go. The next is to use these advances to shed light on the quintessential quality of the future. It differs profoundly from the past. Next section, from this to that. The distinction between past and the future is at once basic and pivotal to human experience. We were born in the past, we will die in the future. In between, we witness innumerable happenings that unfold through a sequence of events that, if considered in reverse order, would appear absurd. Van Gogh painted a starry night, but could not then lift the swirling colors through the reverse brush strokes, restoring a blank canvas. The Titanic scraped along an iceberg and ripped open its hull, but could not then reverse engines, retrace its path, and undo the damage. Each one of us grows and ages, but we cannot then turn back the hands of our internal clocks and reclaim our youth. With irreversibility being so central to how things evolve, you would think we could easily identify its mathematical origin within the laws of physics. Surely, we should be able to point to something specific in the equations that ensures that although things can transform from this to that, the math forbids them from transform from that to this. But for hundreds of years, the equations we have developed have failed to offer us anything of that sort. Instead, as the laws of physics have been continually refined, passing through the hands of Newton, classical mechanics, Maxwell electromagnetism, Einstein relativistic physics, and the dozens of scientists responsible for quantum physics, one feature has remained stable. The laws have steadfastly adhered to a complete insensitivity to what we humans call future and what we call past. Given the state of the world right now, the mathematical equations treat unfolding toward the future or the past in exactly the same way. While that distinction matters to us profoundly so, the laws struck at the differences, assessing it as of no greater consequence than a stadium's game clock ticking off time elapsed or time remaining, which means that if the laws allow for a particular sequence of events to occur, then the laws necessarily permit the reverse sequence too. As a student, when I first learned about this, it struck me as just shy of ludicrous. In the real world, we don't see Olympics divers popping out of a pose, feet first, and landing calmly on springboards. We don't see shards of stained glass jumping up from the floor and reassembling into a Tiffany lamp. Clips from films run in reverse are amusing for the very reason that what we see projected differs so thoroughly from anything we experience. And yet, according to the math, the events depicted in the reverse run clips are fully in keeping with the laws of physics. Why then is our experience so lopsided? Why do we only ever see events unfold in one temporal orientation and never the reverse? A key part of the answer is revealed by the notion of entropy, a concept that will be essential to our understanding of the cosmic unfolding. Let me stop here.